All right, so we have some new stuff here today, and just something different, not necessarily difficult, just something different. So we're basically going to be finding another way to calculate delta H. So hopefully you've kind of seen a pattern here that we're looking at all kinds of different ways to find delta H. So if we kind of look at the terminology here, a couple of things should stand out. And the idea that the word enthalpy and the word energy are going to be the same thing, I think is important. So, like if a question asks you for enthalpy or energy, what are they really going to ask for? Well, they're really asking you for delta H. So I think that it's kind of good to understand what you're looking for. So you're looking for delta H. So remember, delta H is something that is going to be in kilojoules per mole. And we found this with Hess's law. We found this with Q equations and manipulating, Q divided by moles. So now we're going to do it with bonds. And this is honestly easier than what we've done in the first two things. So it says bond enthalpy is, and we need a definition. This is going to be delta H. So there we go. When one, and this is important, 1 mole of bonds is broken in the gas state. So I don't know how important that last part will be for you, but the key piece of information here is this, that we're looking at 1 mole of bonds. We'll look at the delta H, right? It's kilojoules per mole. So that all kind of ties in. All right. So delta H when 1 mole of bonds is broken. So when we start talking about making bonds and breaking bonds, we're going to be looking at the left and the right side of the equation. So think about it this way. You start with some chemicals. You break the bonds. They make new chemicals, and those chemicals form bonds. So in order to break bonds, it says here on B, it says that when bonds are broken or dissociation, the bond energy is always positive. So what does that mean? That means that it takes energy to break a bond. So if you have something like water, it's going to stay water unless you add some type of energy to break the bonds between the hydrogens and the oxygens. So we are breaking apart bonds that already exist. So if you're going to do that, that is going to take or absorb energy. So it's going to take or absorb energy. Like you put it in, so you're putting energy in. And so what that means is that when you're putting the energy in, that's going to be a positive delta H value. Now, when we make new chemicals, then usually for that to happen, they're going to be more stable. They have extra energy, and so then you're going to get a negative delta H because heat is going to be given off. So heat or energy is given off, and so that is given off, or I guess you could say released, but either way, some heat is coming out. So when we do a lot of reactions in class, a lot of times they heat up. And so that's because, got to fit in the word released here. That's because the chemicals we make are more stable. They don't need all of the extra energy, so we feel that. So we feel the heat coming off of them, and they're warm. And so if you look over here on the right, it says an endothermic process involves the separation of particles. So look at that, separation of particles. So we're breaking them apart. So we stick the energy in when we're breaking them apart. And then it says exothermic involve bringing things together. And so it's they don't need all their energy. They're in a better place. And so they release energy. And so for you, it's more about the sign. It's more about the idea of negative sign versus positive sign. Okay, so let's look at the formula here. It's really very simple, super easy. And what the formula says is that delta H is the broken bonds, the bonds you break, plus the bonds you form. So you just add them all up. Okay, now here's the hard part. You're going to have to look at some kind of data. And so we have a data book in IB. So you could get this from the data book. But in IB, a lot of times, they do give you the data sometimes in the question. So sometimes you have to look it up. So the data book, this is something that you would look up. And remember, the data book is something that you have on all of your tests. Now, I don't always have you use it because a lot of times I give you those pieces of data in the problem. But in this particular situation, we are going to use the data book. And so I think on the test, I either give these to you, I give you the data booklet, or like I said, they're provided in the test. And so if we look right here, it says example 9, find delta H, and here it goes, using bond energies. So they want us to use the bonds for this reaction. So I know that you guys don't remember Lewis dot structures, and so you don't quite remember that you would take oxygen and put it together like this, and you'd fill everybody up to 8, and you'd look up oxygen, and you'd be like, oh, oxygen each one has 6 valence electrons, so there's 12 electrons in this thing. You would count these, and you'd be like, okay, 2, 4, 6, 8, 10, 12, 14, that's too many. And so you'd be like, oh, how do I fix that? Well, I put a double bond right here, and then I'm going to get rid of a pair here and a pair here, and then I'm going to end up with something that looks like this. 2, 4. So if I'm counting again, 2, 4, 6, 8, 10, 12. Bingo, it's right. There's the formula. I know you don't remember all that. You did it. I want you to remember that you did it, but right now I will provide the bonds for you. And if there's a question about that, let me know. But I know that that's not something that I want you to have memorized right now. So if we take a look here, we have a formula, and I've given you the different types of bonds. And so what we have to do is we have to figure out what the overall delta H is. So these two chemicals over here, we're going to put energy in, so they're going to have a positive delta H. And then these chemicals over here, it's going to give off energy because it's a product, and it's negative. So basically, reactants are going to be positive and products are going to be negative. So you really have to remember that because the numbers are all positive. So you have to remember, you should probably write this down. that our reactants are going to be positive, and then products are going to be negative, and you have to apply that sign. Okay, so you have to actually put the sign in. Now, the only other thing we have to worry about is right here. If there's a coefficient, you multiply the bonds by that coefficient. So I'm going to go ahead and write a 1/2 right here, not in highlighter. I'm going to go ahead and write a 1/2 right here to remind myself that I need to multiply whatever I put here by 1/2 because I don't have a whole mole. I only have half a mole. Okay, so where the heck are we going to get these numbers? Well, this chart right here is in the data booklet, which is in Schoology. It's just a bunch of pages of different kinds of data. And so if you look at the way the chart reads, we have single bonds in this chart here. So all of these are single bonds. So like fluorine single bonded to chlorine would be 255 kilojoules. And so that's where we'll get the numbers. We'll just use the chart. And then down here, they have some selected multiple bonds. And so those are like doubles and triples. It's like here's a triple bond to nitrogen, a double bond to O, which we're going to actually use that one. So you just look them up on the chart. Now, depending on the chart you have, sometimes the numbers are different. And I've seen that come up before. So like if you have a data booklet and then you're looking this up on the internet, or maybe you have it in another resource, they might be off by like a couple plus or minus, but it's not a big deal. Okay, so let's take a look at what we're looking for. We're looking for a hydrogen single bond, so let's find that over here. So the hydrogen single bond is, then I'll use the highlighter here. So here's the hydrogen single bond. So here's a hydrogen, and then we find the other hydrogen, and we just sort of find where they meet, 436. So the hydrogen is 436, okay? So you just look it up, and then you write down, because it's going to be, remember, the left side is positive because these are reactants. And so I'm going to do 1 times 436. Why am I doing a 1? Because, well, there's a 1 there. So I just want you to get in the habit of multiplying by the correct value. So, okay.